Thank you very much, Mike. It's lovely to be here in Cambridge. I grew up in Cambridge, and it's sort of nostalgic to walk through the streets and realize it doesn't belong to me anymore. I'm at the other place, so forgive me for that. People always say, I'm going to tell the joke about fusion because otherwise somebody in the question time at the end will tell the joke about fusion. People always say that fusion is 30 years away and always will be. It is 30 years away, but I will try and convince you that we're really quite close to being able to do fusion. We're not that close to being able to do fusion in a commercially viable way. And that step probably requires some ideas that we don't really have yet. Now, I ran the British Fusion Program. I ran UKAEA for 9 years. And so that's a real confession because, you know, come out and say, we need some new ideas isn't exactly endearing yourself to your funders. But I think it's important to realize that we've got ideas that can take us to fusion, can make fusion reactions happen, can make us generate energy out of fusion, but we probably need 1, 2, 3, 4 ideas if we really want to make fusion a practical reality that could produce the base load of our electricity generation so that our renewables would work in the best possible way. So the story of fusion goes right back. We always show pictures of the sun. If you go to a talk on nuclear energy and fission, they show pictures of green fields with cows in them. It sort of makes people feel comfortable with nuclear energy. When you talk about fusion, you show a picture of the sun because the sun is a fusion reactor. And we didn't always know this. And the story of fusion really begins with this guy, Sir Arthur Stanley Eddington, great Cambridge astrophysicist, probably the greatest theoretical astrophysicist of the early part of the 20th century. And Eddington was president of the British Association for the Advancement of Science in 1920. And it was in Cardiff. And he gave one of the most remarkable public lectures on science that I think has ever been delivered. It's remarkable, one, for its clarity, but two, for the fact that it's a public lecture, but almost everything that he said was brand new research. And he managed to, to convey this to the audience in the simplest possible terms. And it's a great thing for students to look at because you get this impression when you're a student that, to do good research, you have to cover the board with equations or you have to do something really complicated. No, actually, you just have to think really clearly. And that's what Eddington was doing. So he took as his subject, what's going on inside the sun? What is the sun made of and how does it work? And he said the problem is our current theory of the sun, this is in 1920, is Kelvin's theory. Lord Kelvin had said, the sun works like this. It started as a big ball of gas, which had gravity, and it started to pull itself inwards. As it pulled itself inwards, that potential energy, the gravitational energy, was converted to heat, so the thing got hot. It got hot enough at some point that the pressure pushing outwards balanced the gravity. But then it radiated photons away, light away, and it got cooler, and then it shifted down a little bit further. And it radiated photons away, and it shifted down a little further. It radiated photons away. And gradually it's converting gravitational energy into light. And Kelvin estimated the age of the sun to be about 20 million years. This is about 1862, I think. And that theory prevailed for a long time. And it really annoyed Darwin because he said 20 million years is not long enough. And of course, he thought of it as one of the most profound criticisms of his theory. We come to 1920, and Eddington said, this can't possibly be true. There's all kinds of reasons, geological reasons, beginning of the geological radio evidence, reasons that we see stars in the distance from us that look exactly like our sun, that must be much older than the sun. He said that it just can't possibly be that the sun is 20 million years old. It must be much older than that. And he said, well, if it's much older than that and it's been radiating all this time, there must be some source of energy within the sun. Now, he was very lucky because Aston had perfected mass spectrometry, measuring the masses of the atoms. And he measured very carefully the mass of hydrogen and the mass of helium. And the mass of helium was just a little less than 4 times the mass of hydrogen. Now, this is another lesson about science, really. It's good to be lucky. He was lucky because Aston had just made these measurements when he was thinking about this problem. And so he said, well, look, we look at the atmosphere of the sun, and the atmosphere of the sun shows part of the spectra of hydrogen, the spectra of helium. So we know hydrogen and helium are in the sun. And so what if there's some process that converts hydrogen into helium? You take 4 hydrogens, you put them together somehow, you have to capture 2 of the electrons, and you make helium. Actually, how that happens doesn't really matter, because all we have to know is the mass at the beginning and the mass at the end, and the total difference in the mass times c squared must be the energy released by creating helium out of hydrogen. The mechanism for doing that, he didn't have to understand. You took the 4 hydrogens, you took the helium, and looked at the mass on the left-hand side and the mass on the right-hand side, and you subtracted one from the other and multiplied by c squared, and that's the energy that comes out. So if you took, this is more accurate, 1.008 kilograms of hydrogen and converted it into 1 kilogram of helium, you would produce 7.5 times 10 to the 14 joules of energy. That will supply all your energy needs for about 10,000 years. You as a person, not the world. This is coming from the binding energy of the nucleus. This is coming because you're sticking together the nucleons inside the nucleus. But actually, Eddington didn't even know that there was a thing called a neutron at this point. So he didn't really understand that helium nucleus consists of 2 protons and 2 neutrons. By the way, I'm coloring the protons green and the neutrons blue. It's not their real colors. So he conjectured that this is what the sun was doing. He said, if we took the mass of the sun and we imagined that a third of it is converted from hydrogen to helium, how much energy would that be? And how long could the sun shine with that energy? And he came up with 10 billion years, which is not a bad estimate of the lifetime of the sun, of the age of the sun. It was a pretty good piece of guesswork at the end there as to how much would burn, etc., in order to get the age of the sun. And he was very happy with that result because that kind of fit with the data of the kind of age of the sun as we would do. He went on to conjecture that maybe one day we would use this process, which we now call fusion, nuclear fusion, to make electricity and power the planet. I like the quote, but we still haven't got there. So it's not 30 years away. This was 1920, and we're very rapidly approaching 100 years since then. Actually, thinking about how we might do this, people started to think how you might make fusion reactions happen really during the war. The people who were collected at Los Alamos lab to build the first atomic bomb were probably the greatest collection of physicists and engineers ever put in one place. And they thought about a lot of things. But of course, their main thing was to build the 2 atomic bombs that were dropped on Japan. But at the end of the war, in November of 1945, they decided that everybody was going to return to their universities and back to their day jobs, their civilian jobs. And they've been thinking about all kinds of different things. And so they said, let's have a Demob conference, highly classified conference of all of the people who had worked on the bomb, in which people would get up and say things that they think will be able to be doing in the future. Basically speculative stuff. This was a very classified conference, and I knew about it when I was a student at Princeton in the early 1980s, that this conference had happened, and that at this conference, Enrico Fermi had talked about doing controlled thermonuclear fusion, to try and do this process that happens inside the sun, but in a controlled way. And a friend who was at Los Alamos even went into the classified archives at Los Alamos to try and find, the notes from this meeting. But because it was so classified, no notes were allowed. But by 1945, we British knew that the Americans were going to cut us off from the secret work on the bomb. And indeed, in 1946, the McMahon Act was passed as an act of Congress, and Britain was then cut off from the American nuclear secrets, and not until 1958 did we reconnect again. So the British government was very keen to make sure that all the scientists who came back from Los Alamos would come back with as much information as possible. And so at this conference were quite a few British scientists still in 1945, and this guy, Philip Moon, who ended up being a professor of nuclear physics at Birmingham, was there, and he took notes on Fermi's lecture. And in this lecture, Fermi talked about making a controlled fusion reactor. And I think this is the first time anybody had really ever discussed it. And he talked about the fact that we had to create conditions like the center of the sun, and what would be the processes going on at this time. They were also thinking about how to make hydrogen bombs at that time, which is a kind of fusion. And Moon went back to his room that night and wrote down his recollection and passed it to a member of the Foreign Office who came to visit him in subsequent days, and it was brought back, and it was amongst Sir John Cockcroft's papers in the Churchill Library when a friend of mine researching a book on fusion came across it, gave me a call and said, you've got to come and see this. And it is, I think, you can see it, Churchill Archives Centre, Churchill College, Cambridge. It's the first example of somebody thinking, okay, we know this process happens. How could we make this happen on Earth? And he talks about confining a hot set of fusion fuel with magnetic fields. And it was brought back to England. It sat, you can see what Chadwick, who discovered the neutron, said, these notes and any others on this topic must continue to be classified as secret until further notice. This matter should be handled with the greatest discretion. It was declassified towards the end of the 1950s, but languished in the archive. So we're about to actually do a serious fusion burn. The world is constructing a huge experiment in southern France. Here's a picture of the assembly hall for it. Now, this is ITER. It used to be an acronym, and they removed the dots between the letters because ITER apparently means the way in Latin, and they thought that sounded better than the International Thermonuclear Energy Reactor. This is the assembly hall, and it sits on top of a flattened-off mountain near Aix-en-Provence. If you're going to make an experiment, why not put it in Provence, really? I mean, that sounds like a good place to put it. This is the assembly hall. It is a phenomenal piece of engineering that they are assembling there. There are 7 international partners. Europe is paying for just over 40% of it. The other partners are Japan, India, Korea, Russia, the United States, and I missed one out. China. And all those countries are building bits of it, and it's being assembled in France. It's over budget, of course, and it's late, as all big projects are. It'll probably cost about 15 billion, but the cost is shared. We don't actually know how much it costs, because you only know how much the bit you're building costs. You just have to deliver your bit. So the Chinese have delivered most of their bits, the Russians most of their bits, and the Americans are late. That's the assembly hall. This is actually where the machine is going to sit. It's a donut-shaped machine. I'll explain this in a moment. And it sits right here on top of that kind of structure there. And the actual building in which it sits is 6 stories deep, going downwards from here, and it'll be another 6 stories going upwards from there in terms of the size. What's it going to do? So now we need to understand what really drives fusion. So inside the nucleus of the atom, there are 2 important forces. There are actually 3, but these 2 are the important ones for fusion. There's the normal electrostatic force. There are 2 kinds of particle in the nucleus, the protons and the neutrons. And the protons are positively charged. And every nucleus has positively charged protons in it. The positive charges repel positive charges. So at distance, any 2 nuclei repel each other because of the positive charges. The force that glues the nucleus together is the strong force. And that only happens at short distance. And that's an attractive force that pulls things together. And if you take any 2 nuclei and you bring them close to each other, right, they will repel at distance. And it's only when you get within the distance at which the strong force can act will they pull themselves together and glue together. If you want to make fusion happen, you've got to get over this repulsion. You've got to get over the fact that at distance these repel. So what you really want to do is you want to do fusion. The easiest fusion to do will be between nuclei that have the least repulsion. And that means the least charge. And the least charged nuclei are hydrogen. So if you're thinking about starting out to try and do fusion, stars do fusion between hydrogen, and then they do fusion between helium, and then they do fusion between carbon, and they build up all the elements that we're made of. But if you want to do fusion, the easier fusion reactions to do are the ones between the hydrogen isotopes. Now, hydrogen comes in 3 forms. It comes in your classic ordinary hydrogen, which is 1 proton in the neutron. It comes in heavy hydrogen, which is called deuterium. So do we have a pointer here? Did I? No, never mind. Heavy hydrogen, deuterium, which is 1 proton and 1 neutron. Deuterium is 1 part in 6,000 of the hydrogens in seawater. It can be separated from seawater rather easily, and you can make heavy water from it. There's super heavy hydrogen, which is tritium. Tritium has 1 proton, which are colored green in this picture, and 2 neutrons. And tritium has a half-life of 12.4 years. It doesn't really exist in nature because it decays away and makes helium-3. But the easiest fusion reaction to do by a factor of 100 is between these 2 isotopes of hydrogen. At distance, you've got deuterium, you've got tritium. You bring them towards each other, they repel, they repel, they repel. You get them close enough, the strong force grabs them, pulls them together, and for an instant makes helium-5. Helium-5 has 2 protons and 3 neutrons. But helium-5 isn't stable. It then kicks out one of those neutrons, and it makes ordinary helium, which is helium-4, which is the one up at the top there. which has 2 protons and 2 neutrons. It's called an alpha particle, as well as a helium nucleus, and a neutron. This reaction is by far the easiest fusion reaction to do. The only way we know to get it to happen is to fire deuterium and tritium at each other at speed so that they can come together fast enough that they overcome their repulsion, get close enough, and then you have this rearrangement. They grab each other, make helium-5, spit out helium and a neutron. And the energy comes out as the helium traveling at immense velocities and the neutron traveling at immense velocities. It comes out as the kinetic energy of those products that you get out at the end. You can't actually fire tritium at deuterium. I mean, your aim ain't good enough, right? So what you've got to do is you've got to have your deuterium and tritium moving around at velocities, bumping into each other many times, and normally just glancing off each other. But when they do bump into each other almost smack on, they will fuse. But you have to have enough energy to overcome that repulsion, which means that they must be moving around at speeds equivalent to temperatures of order 100 or 200 million degrees before they have enough kinetic energy that they can get over that repulsion and get close enough to stick. So if you could get deuterium and tritium up to about 200 million degrees, just a pot of deuterium and tritium up to about 200 million degrees, it would burn quite nicely. It would make helium for you. And as it made helium, that helium would come out with immense, and it would be hot itself because the helium is coming out with a phenomenal velocity. That would be great. But actually, how do you make a pot of deuterium and tritium? And most of the rest of this lecture will be talking about how we do that, right? Because it's got to be at 200 million degrees. It ain't easy to hold something at 200 million degrees. There's another problem. This is the easiest fusion reaction to do by a huge factor. But it has a problem in that tritium doesn't exist in nature. So actually, your fusion reactor has to make its own tritium. And you can make tritium if you bombard an isotope of lithium with a neutron, and it splits into tritium and helium, and that tritium goes back in your reactor. And here's the first sort of real advantages of why we want to do fusion. There is enough, well, so one of the advantages is that deuterium isn't radioactive, lithium isn't radioactive, and so the only thing radioactive in this, neither is the helium that is produced. Only thing that's radioactive in this process is the tritium, which you make and consume. Well, that's very nice. How much do we actually have of the fuel? There's enough deuterium in seawater to power the whole of our energy needs for 60 billion years. Now, the Earth is going to be eaten by the sun in about 5 billion years, so it's overkill. There is enough lithium in seawater to power the planet for about 30 to 50 million years. So if we can only do this fusion reaction for the next 30 or so million years. It ought to be enough time for us to get to do more difficult fusion reactions after that. This is actually an easy reaction to do. If you've got that neutron, doing this reaction is really easy because the neutron is not repelled by the nucleus because it's not charged, and so it just goes straight in, hits the lithium, and makes that happen. The hard thing is making the deuterium and tritium hot enough that you can make that reaction happen. Typical power density you can get. So supposing you have this pot of deuterium and tritium at a pressure. What's the sort of powers you can get out of it? Well, you can get about the power density, I'll have this formula slightly different on the next page, but is proportional to the pressure in atmosphere squared times about 1/10. And that is in megawatts per meter cubed. So imagine I could hold this thing at a few atmospheres of pressure. I'm making power of order a megawatt per meter cubed. So if you want to make a gigawatt reactor, you've got to have, you've got to have about 1,000 cubic meter reactor, which is 10 by 10 by 10 meters. So it's possible that this reaction would actually, get you to a commercial scale reactor. I think I've said all those things. This is actually a more precise version of that formula, right? That the power density in megawatts per meter cubed is 0.008 times p squared in atmospheres. Now, in the middle of ITER, which I'll describe in a moment, the pressure in the deuterium and tritium will be about 7 atmospheres. So that's 49, and that gives you about 4 megawatts per cubic meter. That's the kind of power densities you'd need to make a commercial reactor. So it's we're already seeing that this has the possibility of scaling to that. Now, I did say there was a problem with this reaction. Producing tritium and consuming tritium is an extra complication. And you might say, can't we do a reaction that doesn't have that extra complication? This is the reaction rate going up here, forget about the units, in terms of the temperature of your fuels. And you can see that this is the deuterium-tritium reaction. This is the deuterium reacting with itself, and this is deuterium with helium-3, and this is protons with boron. You really don't want to try to do something else if you're just starting out in fusion except deuterium-tritium. There's a factor of 100 on the reaction rate there at its peak. There is a company called Tri-Alpha, which I'm told has raised about $2 billion in venture capital in Irvine, California, which is trying to build a reactor using this green line, proton-boron. That's proton plus boron-11 goes to 3 heliums. That's why it's called Tri-Alpha particle. And they've got investors. So what will ITER do? How do we put deuterium and tritium and hold it there while it does fusion reactions? There's actually 2 ways that people are trying to do this. You could imagine somehow holding deuterium and tritium with a magnetic field so that it doesn't touch the wall of a container. Holding it in space so that it can get to these immense temperatures and just holding it steady and letting it do that. That's what I'll describe. There is another way, and that is, if you make the fusion happen really, really rapidly, it will blow itself apart, and you can make little mini explosions of fusion. And people are trying to do that using the world's biggest laser in Lawrence Livermore Lab in the States. And I won't describe that because it will take me too far from the central theme of my talk. So ITER, here's a picture of ITER. Here's an engineering picture of ITER. The yellow hole is a donut-shaped hole. Those tiles on the wall there are actually beryllium tiles. The yellow is the beryllium tiles on the wall. Down here is tungsten exhaust system. These gray things here are niobium tin superconducting magnets. They make a magnetic field at the center of the device of 5.2 Tesla. On the magnet on this side here, they make a field of 11.8 Tesla. That is right at the limit of superconducting technology. They are 12 meters tall, but we've made 3 of the 12 coils that's going around there already. But they're the largest superconducting magnets that have ever been built. 11.8 Tesla, the forces equivalent to about 500 to 600 atmospheres of pressure on the inside of that magnet. When you think that the pressure at the bottom of the Marianas Trench in the Pacific Ocean is 1,000 atmospheres of pressure, you've got very, very serious pressures on the inside of these magnets. So the steel structure that holds the niobium tin in the superconductor there is immense. That magnetic field produces a field that goes around the torus. You then put your deuterium and tritium into that yellow hole. This solenoid here is a superconducting solenoid. You swing the voltage in that superconducting solenoid, which changes the magnetic flux through the middle. And any physics student will tell you if you change the magnetic flux through a loop, you'll produce a voltage round the loop. And that voltage round the loop is a few volts around the inside of the yellow cavity. That few volts breaks down your deuterium and tritium gas, which is sitting in there, and makes it into a plasma. So the electrons are ripped off the atoms. They start to move in one direction, and the positive charges start to move in the other direction. And you induce, in this case, about 15 million amps to flow round the circuit inside the yellow hole. The 15 million amps converts the field, which just went round like that, into a field with twist in it. Now, if you've got current, you have two wires of current, it attracts. Light currents attract. Remember that from A-level physics, those of us who did A-level physics. Light currents attract. So you've got a big wadge of current flowing around that, and one side of the current attracts the other side of the current, because they're going in the same direction. And so those light currents attracting causes what we call the pinch effect. The plasma, which is this ionized gas of deuterium and tritium, with this huge current in it, attracts itself. And it pulls itself off the wall and into the middle of that cavity. So now you have your deuterium and tritium suspended with magnetic field wrapped around it in a kind of cage-like structure in the middle of your vessel. You then turn on some enormous beams, and you can see the edge of the beams coming in here. Those beams bombard the plasma with energetic particles to heat it and take the temperature up to 100, 200. Operating temperatures in the middle of ITER will be about 230, 250 million degrees. When you get to those temperatures, instead of just glancing off each other, the deuterium and tritium will start to react. And inside this cavity here, you will start to generate fusion energy. This is the typical orbit of one of the helium atoms that you produce inside that cavity. So you have this fusion reaction, out spits helium nucleus and a neutron. The neutron, it's not charged. It crosses the magnetic field and bangs into the wall. The charged particle, the helium nucleus, is captured by the magnetic field, and it makes these kind of orbits inside. As it's doing that, it's traveling through the plasma, smashing into deuterium and tritium as it goes, because it's moving very fast, giving up its energy to the plasma. So if you can get your plasma to this temperature, and it starts to make fusion, it will start to make heat that's contained inside the plasma. It's a bit like a fire. Because now that you've lit the fire, it is making heat, which heats itself. We've managed to make fusion happen in jet at Cowley, just south of Oxford. But we've never managed to make the fusion reactions be strong enough that they self-heat the plasma. Until you get that, you don't really have a burn. Because at the moment you take away the heat that you supply, it will go out. But if you managed to get the helium, enough fusion going, that you've got lots of these helium nuclei plowing through the plasma, heating the plasma, you can get it to self-heat itself, and you can get it to actually what we call ignite. So the analogy is basically, you know, if you have a gas poker and you have some sort of wet, dampish wood in your fire, you can get the fire to start burning. You've got your gas poker on it. You put it in there, you fire up the gas poker, and the wood will burn. It's what we call a wet wood burner. It will burn, but you switch off the gas poker, it'll go out. If you've got enough burning happening, the heat generated by the burning will cause the rest of the fire to light up too. And then all you have to do is to keep feeding it more wood, and it will keep going. This is what we would like to do at the next stage of fusion, because we've never done that. And that sort of burning plasma situation is sort of the scientific proof that we could make fusion happen. That's the goal of ITER. That's why 7 countries around the world, well, I'm treating the EU as a country, I'm sure that's wrong right now, are investing in this very expensive experiment. I'm going to do a little bit to explain to you what are the factors that determine how well this will go. Okay, because it sounds sort of magical that you just sort of stick some deuterium, tritium in there, you pass a huge electric current through it, gets hot, and it's going to make some fusion. So the power, again, I had this formula before, that's the power density. One way of thinking how the magnetic field holds the plasma is just the name for the ionized deuterium and tritium, is that the magnetic field pushes on it with a pressure. It has a pressure. Typically in ITER, there'll be about 0.1 grams of deuterium and tritium inside 800 cubic meters of vacuum vessel. So it's very, very diffuse. But it's at such an immense temperature, it has a pressure of 7 atmospheres. So the pressure in here has to be pushed on by the magnetic field pressure. And a good formula for the magnetic field pressure is 4 times the magnetic field squared in Tesla. So I said you had about a 5 Tesla in the middle, so B squared is 25, and 4 times that is 100 atmospheres of pressure from the magnetic field in the middle. It's 400 atmospheres at the edge of the coil, and about 400 in the middle. That's the pressure pushing on the plasma. And there's a ratio of the pressure you can get in your deuterium and tritium, which is what you want, and the pressure in the magnetic field. And if you've got a good magnetic bottle, that would be 1. But it's not. The best we are capable of doing is less than 10%. So this ratio is kind of a figure of merit of how good your magnetic field is at holding your deuterium and tritium there, beta. And we can rearrange that formula as beta squared times b to the 4th. This is where all the cleverness goes. If you've got a good magnetic bottle, if the magnetic field line is are confining it well, we might expect betas, 0.1, 0.2, 0.3. Bad confinement is about 0.03, 0.01, 1%. And the power in the fusion is going to be proportional to the square of that, and then the 4th power of the magnetic field. Magnetic field, you get from the coils. Superconducting magnets can only deliver so much magnetic field. The technology will only stretch right to the level at which ITER is doing at the moment. We're at the outer extreme of where we could do that. So we want fusion power out of this thing. This is physics. This is engineering. Just engineering. So in the middle of that device, calculations show. So now I've colored where the plasma is pink. I keep making the joke that it's pink, just like the British Empire, but nobody gets the joke anymore. So the plasma there, the typical power levels we're expecting from it is about 500 megawatts of fusion power from the whole thing, about half a gigawatt of fusion power in ITER. Because when deuterium and tritium react, they make this helium nucleus plus the neutron. 1/5 of the power is in the helium nucleus, and 4/5 is in the neutron. This is the bit that stays in, this is the bit that leaves. So about 100 megawatts of heating power from the fusion reactions itself. 400 megawatts of neutron power that just goes across the magnetic field and embeds itself in the wall. And ITER will have lithium in the wall to try out the whole process of making your tritium from the lithium in the wall. But that's a sort of subsidiary experiment to the primary experiment, which is trying to get the fusion burn to happen inside there. So we've got about 100 megawatts of heating power from the fusion reactions itself. It has an external heating, the external beams that come in like this, of about 50 megawatts. So if we can get the fusion reactions going, the self-heating is determined to be the most important part of the heating. There is some effort now to maybe push this up, just in case we haven't done our calculations well enough, and we might need more power than that. Now, there's a very important concept on this. Here's your plasma. Inside here, it's heating itself due to the fusion reactions. But heat is leaking across the magnetic field. We have never been able to make perfect magnetic bottles. We're about 1,000 off the theoretical low leakage limit, low limit. We're about 1,000 times more leakage of heat from this bottle than would be if it were perfect. What's happening inside here is that turbulence is moving the heat from the middle to the outside, and the bottle is leaking. The magnetic field is kind of not holding it as perfectly as we want it to do. And to describe that, has only the last 10, 15 years have we understood the turbulence that causes that leakage of heat. It's been a major effort across the world to understand how this thing that's at 100 million degrees is causing turbulence that leaks the heat to the outside. The hot stuff starts to come out, the cold stuff starts to come in, and it's exchanging itself and working its way to the outside. So that leakage of heat we normally characterize by a number. It's called tau E. It's the time it takes the heat to go from the center to the outside of the plasma. And on JET is the biggest machine we have at the moment, it's the precursor to ITER, it's about a second. On ITER, it has to be about 4 seconds if ITER is to get to this burning state. It depends on the size, because it takes longer if the machine is bigger. And it depends on the strength of the magnetic field, and I'll get to that towards the end. But it's, for many years, and we've been trying to do fusion for a lot longer than 30 years, for many years we've just characterized it as this number, and we've done empirical fits to all the data to try and understand that number. In the last 15 years, we've been able to calculate it, and I'll describe that in a moment. Nobody has promised that ITER will actually entirely burn. Ignition would be, you put your deuterium and tritium in, you heat it up, you get to this stage, it self-heats, you turn off your external heaters, and you're not putting any energy in, and it's just giving you energy out. What we've promised is that we'll get 10 times more energy out than we put in. That's what we've promised. I'll show you some calculations in a moment that suggest we might do better than that. So that energy confinement time can be written in this way. It says the power lost by transport from the plasma, that's the power coming out of the plasma because of leakage, is the stored energy in the plasma divided by this time. Simple formula. Now, we know that if we're going to be self-heated, that power has to be given by my formula proportional to P squared. So you put these two things together, and you say, well, in order to be self-heated, the pressure times this time has to actually, in these units, that's atmospheres, that's seconds, has to be bigger than 20. On jet, we're at about 6. So we haven't got up close, to 20 yet, but the idea of ITER is that we beat this threshold. But it's self-heated, that it heats itself. I've put the same formula using this ratio of the pressure to the magnetic field pressure, just so you can see it's better if we can have more magnetic field and better if we can confine better. So about in the 90s, computers got big enough and our calculations got good enough that we started to be able to calculate the actual behavior inside the plasma. There are, of course, something approaching, it's about 10 to the 21 particles inside any one of these devices. But on a modern computer, you can simulate the motion of about 10 to the 10 to the 11 particles. So about 10 billion to 100 billion particles can be simulated on one of these enormous computers. You follow them, they're charged particles, so each one carries a charge with it, each one makes a current, and you solve for the electric and the magnetic fields that they produce. And if you do that on a very large computer, you can actually simulate the behavior of the plasma in some detail. Now, it's a lot more complicated than that, because if you just did that, the computer would crash. And it did many times when we started doing this. But with a bunch of approximations on how it works, we're able to start a simulation like this one, which is, let's go backwards, okay. So this simulation is started in which we loaded all the particles up smoothly inside it. You can see that the turbulence starts to see the striations of the magnetic field lines, and you can see the rotation that's induced inside the deuterium and the tritium. And what you can see is the middle here is hot, and the outside is cold because it's next to the wall. And that temperature gradient across here, in the middle here, it's about 200 million degrees, and at the edge here, it's about 10,000 degrees. And that difference is causing convective transport. Just like when you put, saucepan on the stove, you heat the bottom of it, it starts to bubble and turbulent, and it starts to bubble and ooze across. That's happening here, except that this is not water. This is deuterium and tritium nuclei flying around the place, moving around, and what I'm imaging is the density of particles at any one time inside that. But from these calculations, we're then able to calculate the rate at which hot stuff works its way out by all these little swirls to the edge, and cold stuff comes in from the edge towards the middle. And that's the loss of heat. Of course, that's the loss of heat we want to replace by doing fusion. So it's that replacing of the heat that's generated, the heat that's lost through turbulence by fusion, which is the key process that we have to overcome to make fusion really happen. I think I'm going to leave this alone right now. So here's a simulation of ITER. This simulation is a sort of meta-simulation. You take those simulations that I just showed you, which are the basic building blocks, and from that you create a law that says this is the rate at which energy is lost from the plasma given various quantities inside the plasma. You then use that within a simulation of the whole machine to see how it's going to actually perform when you start it up. And this simulation was done by a friend from Princeton, and it's been benchmarked against the experiments that we have done in this country at JET. So let me explain what's happening. Along here is time. And up here is fusion power. And this is a bunch of different scenarios for the operation of the machine. We're trying to figure out, when we've got this machine built, how is it we're going to operate it so that we'll get the best performance out of it? And so the simulations are partly teaching us and partly convincing the politicians to build the machine, actually. So here you are at the beginning. In that big yellow hole, you put your deuterium and tritium. Right at this point here, you start to induce the 15 million amps to go around the circuit. So the 15 million amps of current goes around the donut-shaped plasma, and the plasma forms, and the magnetic cage forms around it. 15 million amps typically will heat the plasma up to about 10 million degrees, and really not a lot more. At this time here, you put on 70 megawatts of energetic beams from an accelerator that come into the plasma and bombard it. And those particles smash in to the particles inside the plasma and give it the 70 megawatts of heat. At that point, the central temperature shoots up to, let's look at the blue line, because it's a nice optimistic line. The blue line, scan 2, shoots up typically in the middle to about 230, 240 million degrees. There are a bunch of oscillations here. You can see the blue line doing this. And you can see now we're hitting about 500 to 600 megawatts of fusion power coming out of it. Because now the temperature's gone up, the deuterium and tritium are banging into each other and sticking and making the fusion reactions happen. At that point, the fusion power, which is over 500 megawatts, is self-heating the plasma at about 100 megawatts. So what I'm putting in is 70 megawatts. It's heating itself with 100 megawatts. And so the total heating is 170 megawatts. At this point, we step down the external heating. You can see that it continues to rise up there. These internal oscillations, I'm not going to describe them, but are kind of internal oscillation of the plasma, down to 50 megawatts. And at 400 seconds in, we switch off the external heating. Then in scan 2, it goes into steady state. This is an ignited state. It's putting out just over 500 megawatts of fusion power, and we're putting no heat in whatsoever. If it does that, if ITER does that, that will be the historic experiment. That'll be the first time we've made the essential process that powers the stars in a controlled way on Earth. Of course, it's an experiment. And what you have to do, scan 2 involves the most probable model, because there's some uncertainty in the modeling. I mean, to describe this very complicated situation, the models are not perfectly right. So what we have to do for the politicians and for ourselves is degrade the models and ask what happens if we're not quite right by 10, 20, 30%. So scan 3 here was a degradation of the model by 10%. It's perilously close to not being a success. I mean, we don't reach the goal of 500 megawatts. We do reach self-sustainment. This is ignition here. 20%, scan 1. You build a 15 billion experiment and you get scan 1. You keep telling people tomorrow it'll work, it'll be fine. This is a 20% 1% degradation of one of the boundary conditions. It's very delicate. We need to understand more, probably, before we operate this machine to make sure that we're actually going to get SCAN 2. I mean, SCAN 2 is the most probable model, as we define it. But we are in this land where we're extraordinarily sensitive to the assumptions in the model. SCAN 4 is a disaster. I'll tell you what SCAN 4 is. It's actually a different scenario. You make helium. And one of the things you want your turbulence to do is to flush the helium out. Because helium is the ash of the fusion reaction. And it doesn't react. And if you get more helium than deuterium or tritium, your ash has swallowed up your fire. And if it's not flushed out by the leaky bottle and accumulates, then your fire will go out. And so what we did in SCAN 4 is we turned off the turns in the equations that would flush the helium. And sure enough, you got fusion to happen. This was fine. But the helium accumulates and accumulates, and suddenly the whole thing goes out. That, too, would be a disaster. This experiment's supposed to start in 2025. This kind of shot, probably around 2030, because you're not going to turn it on and turn everything up to 11. You're going to turn the machine on, you're going to learn a little bit about it, you're going to probably have a few mistakes, and etc. So it'll probably 5 years in before we're actually doing these shots. I'd like to be in the control room in Aix-en-Provence watching it burn like SCAN 2, because that'll be the historic moment for fusion. That'll be the moment in which we demonstrate that you can actually sustain the kind of reaction that happens in stars on Earth, hold it steady, make much more energy than you consume. It will be the scientific demonstration of fusion. The machine's costing about 15 billion euro. And if it were a power station, 500 megawatts of fusion power would give you, well, about, if you're lucky, 200 megawatts of electricity, because out comes this fusion, it heats the wall, you boil some water, and you power a steam turbine. That's how we're intending to make electricity out of this. So you might make 200 megawatts of fusion electricity out of this. 15 billion is a lot to pay for 200 megawatts of electricity. It's very big and very complicated at the moment. And we need to think how we're going to go from demonstrating. I'm going to assume that this is going to work. Because I've looked at a lot of calculations, and I think that we have a margin of error there that it's going to work. We're going to demonstrate that fusion can happen, that we can sustain a fusion reaction, historic experiment, everything like that. But this won't be what we're in it for. It won't be the commercial reactor that people want to buy and operate day in, day out. It's got to be smaller, faster, and cheaper. So how do we do that? So one of the things, I was going to show you a little bit of JET data to show you that we've done some of this. This is the inside of JET, which is half the size of ITER. So probably in today's dollars would cost you a couple of billion, not 15. It's 10 miles south of Oxford. It's still the world's best fusion experiment. This is the robotic arms that fix the inside of JET, and we do all the maintenance with robotic arms inside JET. You can see this wall down here. This is tungsten here. This is beryllium tiles along. It's just been modified about 5 years ago while I was the director to the current state. And we're about to do some fusion power shots again. For the last decade, JET has not worked with fusion fuels. It has just used deuterium. Because once you put tritium into JET, it starts to produce neutrons. It becomes a nuclear facility. It's hard to do the experiment. But the results of the last few years have been good enough that we think we can go in and break our own records again. So it was going to be 2018, and I changed the date because now it's been put back to 2019. Introduce tritium. The previous record is from 97. We did similar shots in 2003. Was 16 megawatts for about 1.5 seconds on jet. That's the world record for fusion. We can't operate jet for more than about 6 seconds because it doesn't have superconducting magnets, and the copper magnets get really hot if you run at full power. And so basically we run 6 seconds. And the actual sustained fusion power from jet is more like 4.5 megawatts, and then closing it down. This went up, then it disrupted. The plasma threw itself against the wall. Now, what we expect to be able to do in 2019 is take it up to about 17 to 20 megawatts, sustain it for 6 seconds, and bring it back down again. And so the fusion power record will be broken by ourselves again, I think, in that time. Jet, because it's half the size of ITER, can't tell you exactly how ITER is going to work, but it is the wind tunnel for how ITER is going to work. And so it, at the moment, is set up to be as almost identical in shape as ITER, so that we can do a sort of scale up to ITER from how jet is at the moment. Smaller, faster, cheaper. So if you could make a magnetic bottle that doesn't leak, a fusion reactor would fit between here and there. If you could make a magnetic bottle that is not turbulent, then roughly the distance across the plasma would be about 50 centimeters. And that would be big enough to ignite. Way back in the early 1960s, people calculated this kind of limit, and they said, wow, we can make small fusion reactors, we can make fusion reactors at the 100 megawatt scale. Electricity companies are going to love these things. We have never conquered the problem of suppressing the bubbling of the plasma. It's a hugely complicated thing, plasma turbulence. It's it's particles rushing all over the place. It's electric and magnetic fields. It's very complicated. However, we don't know that there isn't a configuration in which you could make it with no turbulence. We don't know what we don't know, really. There have been occasions when we have found that bits of jet's plasma have no turbulence in them. And what we noticed was when we rotated the plasma at supersonic speeds, where we had a shear in the rotation, then the turbulence went away. These were called transport barriers, and they spontaneously happened in the experiments, and then the theoreticians explained them. I'm a theoretician. And so those regions produced immensely good confinement. And in fact, if we could make the whole of the plasma have zero turbulence, then jet would ignite, and we'd have done fusion by now. What we also realized is that the configuration of the magnetic field, the turbulence can be stabilized by shearing a sheared rotation of the plasma if the magnetic field points in certain directions. And therefore, we started in the 90s and the early 2000s to look at configurations in which the magnetic field looks more like this. Instead of a bicycle tire-like shape, something that looks more like a cored apple than a bicycle tire, in which the magnetic field lines were deliberately designed themselves to have shear in them. This comes from distributing the current in a rather exquisite way. We found, then running turbulence simulations on this, and this was a case that we did about 8 years ago, that the turbulence was hugely suppressed. Not eliminated, but hugely suppressed. and that in a much smaller device, we might be able to get the kind of confinement that we can only get by going to the huge size of ITER. This was called the spherical tokamak, and we built a device, well, we first built a device in a tin can, basically, in the late 90s. In big government labs, there are a lot of tin cans lying around the place, and we built a device that we cobbled together with old coils and things like that, and tested it. It worked quite well, actually, but we were given money in around 2000 to build this device here. Here's a picture of the actual plasma inside it. This is just deuterium, no tritium. We're not actually trying to do fusion here. We're just trying to demonstrate we can make a better magnetic bottle. What you can see now is the turbulence, and you see a flash right there. In a moment, there you see the turbulence has been stabilized. You can actually see from this, by the way, is very, very fast video. This is microseconds in here. And you can see that we have stabilized the bubbling. What's happening, you can't see this in the picture, is that there are beams coming in to produce rotation inside here. This is toroidal. This is the post up the middle. And when the velocity of the rotation hits the critical point, we see a transition into a turbulence-free state. So 4.5, 5 years ago, we started to calculate these states. And this is a calculation, well, which is momentum flux, and that's heat flux. And you want to minimize these turbulent fluxes, and this is rotation rate, basically, along here. And you want to hit this spot here. You want to hit this spot here, where there is zero turbulent momentum and heat flux. And if you can hit that perfect spot, then you have the perfect bottle. These were calculations done by the Oxford group at the time, and it's these red lines I want you to look at. There's a spot here that we're trying to hit. Well, we persuaded the Research Council to fund an upgrade of that device that I just showed you the video of. That device was called MAST, the Mega Amp Spherical Tokamak. And we got 40 million from EPSRC. And we are about to go into commissioning on this device. Here's the... Sorry about the music. This was taking down the old device. This is taking the lid off the old device. We used the bits of the old device for building the new one. This is the original core coming out from the old device. We worked very, very quickly at UKAE. We cut a hole in the shielding wall there with a diamond saw. We took out the original core. We rebuilt the bottom and the top of the device. Now, because this device is going to produce much more heat in a much smaller volume, it has to have a much better exhaust system. This is the top coming off. No, sorry, that's the top. That's the bottom going back in. Here's the vacuum vessel coming back in. These are the cassettes of coils going into the top of the device. I don't know, I should have turned the sound off. It's driving me nuts right now. That's the look from the top. Now, it's going into commissioning. We started commissioning. There were a few hiccups, but it's going back into commissioning. Should be seeing some results early in the new year. It'll take probably a year before we see whether we can hit that sweet spot on the transport. But I'm sort of confident that we have a route to a smaller, faster, cheaper solution through this. That's the British way. I'll show you what the Americans are thinking about to go smaller, faster, cheaper. And that is to push the magnetic field up. This is the solution at MIT, where they want to go to having 23 Tesla on the coil right here. Now, 23 Tesla is equivalent to a pressure of 2,000 atmospheres. so twice the pressure at the bottom of the Pacific Ocean. But if you do that, you can reduce the size of your plasma quite considerably. And this is the proposal from MIT, and they're seeking venture capital money to build this device right now. And I think it'd be interesting to do. I'm a bit worried that with all that pressure, you'll build it and you'll turn it on and it'll just, but. I'm quoted as saying fusion is the perfect energy source. In many ways it is. We've got lots of fuel. It doesn't produce a waste problem of any kind, no CO2. It's very safe. You can do it close to built-up areas. It's got all these great advantages. It's one real problem. It's really hard to do. But when we know how to do it, we'll never not know how to do it. And probably we need a few new ideas that will push us forward. There are huge numbers of startups out there right now pushing fusion ideas, most of which, frankly, don't work on paper, let alone in practice. But fusion is such a tantalizing goal, and it's one of the few things that I can think of that humans have tried to do and we can't do yet. And so if you're thinking about anything, think about fusion, because when we can do it, it will be amazing. Thank you very much.
Well, that was stunning, Stephen. You probably heard that before. I thought I heard everybody stop breathing halfway through that. It was so magical. And if you ever wanted to hear something about the application of research and the challenges of it, you have it. Well, I know there are going to be questions, so the trick is you have to catch my eye and I have to like you. Yep, please, gentleman there. Sorry.
So polywell fusion is this idea that you can do it with a sort of spherical electrostatic trap, which is, the idea is basically that you confine the ions on orbits that go in and out of a spherical thing, but it's got to have an electrode inside the plasma. So at low temperatures, this is fine, but as you get to high temperatures, if you put your hand inside jet, the power flux to your hand is about 10 to the 14 watts per meter squared. There's an electrode on the outer side of it.
Yeah, but not in the center.
Not in the center, but the ions have to go out and back in again. Yeah. The heat flux to that, there's a great paper from a guy who was at MIT just saying, at low temperature, you're fine. You heat the temperature up and the electrode will melt. Otherwise, you won't get fusion. Polywell has never been possible to get to fusion temperatures. It's just impossible.
Here we are. A gentleman in the middle here with a splendid beard. Andrew, just forward from where you are, thanks.
Hi, Steve. It's Steve Smith. You know me. I'm not going to ask you the question, what do you think of our local efforts? But I do have one really specific question to ask. I know the Mars vessel weighed 60 tons, yet you seem to have lifted it with a 50-ton rated crane.
Yeah.
How?
Well, we did actually get the crane rating up a bit. We couldn't put all of the things inside the vessel before we carried it. So that you'll see the upper cassette and the lower, so it was put into pieces. There was a little bit of they didn't invite the director in on the day they carried it in. They thought they'd do it quietly and then declare success, but it wasn't over the rating of the crane. I can't remember what the crane was rated up to, but it was enough to just carry the vessel.
Gentleman up the aisle there on the left-hand side with the white shirt. Thank you. Please put your hands up before you're ready to speak, and I can try and line you up.
Sure. You're producing this flux of high-energy neutrons. I know some of them you're going to consume anyway, but do they not damage all the steel components and the...
Yeah, they do. Every atom in the wall, if the machine is producing 1 megawatt per square meter of neutrons on the wall, every atom in the wall will move 10 times a year, because the neutrons will bang into it and the nuclei will recoil. What that does is it makes little melt spots inside the steel. And those melt spots then re-solidify. And the question is, do they re-solidify in a strong state or in a weak state? And the jury is somewhat out on that. I mean, we know that the gradual accumulation of helium as bubbles inside there will be a problem. But the actual movement of the atoms themselves is not quite clear at this time. We think that what's called displacements per atom, the number of times that each atom can be displaced, can be taken up into the 20 to 30 range without any problems. But a typical fusion reactor will probably have to have hundreds of displacements per atom, or we'll have to have easily replaceable walls. I mean, the way fission reactors get around this is they have rods, and those rods have cladding on them, and when the cladding has been too damaged, you take it out and redo it. And the same may be the solution for a fusion reactor, that you have a very easily replaceable system of walls that you slide out and you put in. Let's get the fusion reaction going before we even worry about that. I'd love to have 100 displacements per atom in the wall. That would really be success. I can't imagine that we can't come up with an engineering configuration. I'm a bit worried that we won't come up with a miracle material that just survives being bombarded forever, which a certain part of the community is looking for that sort of miracle material, and I'm not sure it exists.
Gentleman in the middle there, down a bit, Andrew, down a bit further. And then after that, the gentleman with the blue shirt just behind where Andrew is now. Yeah.
Thanks very much indeed for that. What are your views on, and I know you're probably going to wince when I say this, Lockheed Skunk Works alleged, I know, shipping container-sized 100 megawatt high beta reactor?
So, yes. So when Lockheed made its announcement, they had yet to construct their experiment. And they have the same problem that you have with a lot of these. So they were going to have the superconducting magnets inside the plasma, so that the plasma would go round the coil. Now, the problem with that is you've got to support the coil somewhere. So the plasma will impinge on the supports. And plasmas at these temperatures have phenomenal heat fluxes. So if it bumps into a piece of wall, it'll erode that wall at an incredible rate. So that's one problem. The second problem is that the superconductor has to be shielded from the neutrons. Because if a hot neutron comes into a superconductor, it makes a hot spot in the superconductor. It ain't a superconductor anymore, right? So you have to put about 1 meter of shielding on any superconductor around a fusion reactor. It's difficult to see how you can do that inside a fighter jet. You know, have a coil that itself is 1 meter in diameter with 1 meter of shielding on top of it inside your plasma. I mean, it's bonkers. And so they have started their experiment, and at the moment it is sort of the temperatures of, 3 or 4 times that of a fluorescent light bulb. I am in a catty mood this evening, I have to say, but it was a brave decision to announce that they'd made a breakthrough before they'd actually run the experiment.
Yes, or bonkers, as you say, a good technical term there. Gentleman just to your right, Andrew, and then it'll be the last question, I'm afraid, with your hand up now.
If you were able to get a perfect bottle, how would you get rid of the excess helium from the reaction?
Yes, the helium, we have come up with a way that, so the helium, because it's actually more energetic, has bigger orbits around the magnetic field line. Charged particles go in spirals around the magnetic field line. And because it does, you can interact with it selectively with radio frequency. So there are ways to kick it out if you had perfect confinement. But it is an issue. You would have to actively try and flush out the helium every now and again. So you would have to come up with a scheme to do that. But we don't, unfortunately, have that problem.
With a big project like this, at some point you obviously have to freeze the design and get on with it. And with ITER, most of those design freezers long in the past. If you're freezing the design today, with the benefit of the extra knowledge you've got, what would be the main changes you would make?
So we are actually built, so ITER came to Europe. And as a consolation prize, Europe is building a machine with the Japanese and Japan, which is not going to be a machine that does fusion, but just studies confinement. It's called JT60 Super Upgrade, super advanced. We never called anything mediocrely advanced. But this machine was designed later than ITER, and it's somewhere between the design of ITER and the design of the spherical tokamak that I showed you. It is pushing towards this more compact design. It is more like the cord apple, but it's sort of halfway in between. And I think that if we were designing ITER today, we probably would do that with it, because the advantages of squashing are considerable in terms of performance. We've shown that with experiments at Helium. It really was a Helium idea. They're building one at Princeton at the moment that's like the Helium one. But the one they're building in Japan is sort of a hybrid between the two. And I think that's probably what we would do now. But we fixed the design of ITER, well, we fixed the basic conceptual design of ITER about 15 years ago. It's very frustrating to work in a field in which, it takes decades to get a machine built. And part of the problem, of course, is this is all project management. And getting and managing a project across all the continents of the world with engineers in different places and design centers in different places is phenomenally hard. And I just wish, when I started as director of Helium in 2008, they said, ITER will be working by 2016. It's later, isn't it? Yeah. It's not working yet. And it's proved that the technology really is very hard. Those big superconducting magnets are phenomenal pieces of technology. They have to take so much stress. An niobium tin is some horrendous ceramic type thing that's very brittle, and it has to be held in a matrix of copper and steel in order that it is stable and will work at these pressures. So building the machine isn't a case of ordering stuff. You have to do the R&D in order to build every piece of the machine, and it's just taking a long time.
Stephen, I know there are going to be more questions. That was an absolute model of clarity, so much so that I think we probably almost think we understand, but please don't ask us any hard questions because we wouldn't be able to answer them. An absolute delight. Thank you very much indeed.